Hi everyone. This is another video on the data analysis for Lab 3, particle size analysis. We'll be going over how to do the data analysis on this example data set. Alright, I'm also going to go over how to calculate this fraction retained and fraction passing in Excel. Let's start out by inputting the data. So what I'm going to do is put sieve size and percent in class. So our sieve size, we're not going to use this first row here. The fraction passing is 100%, right? That doesn't really tell us anything. If we got a sieve size with 1 meter holes and we said 100% or the whole sample is passing that size, that doesn't tell us anything. It's going to throw off our regression, and some of these equations won't work if you put a value of 1 or 100% in them. So we're going to kind of ignore this row, this first row. You use it for calculating average size in class, but for these fitting constants we're not going to use it. So starting with the second row, our sieve sizes are 75, 19, 4, 1, 0.6, 0.125, and 0.063. And we're also going to need some data for the pan in our calculations. Percent in class. So starting from the second row again, we have 4.7, 14.4, 20.7, 17.5, 7.1, 13.6, 6.2, and 15.8. Alright. Now when you're calculating these percent in class values, if there was another column here with the weights in each class, you would calculate it as a percent of the total weights from weighing your sieves. You wouldn't use that initial weight before sieving. So all of these percent in classes, they add up to 100. You can see down here it says sum 100. Alright, to do the regression we need to work in fractions though. So let's just convert this to fraction in class. And to do that we just divide our percents by 100. Alright, now for fraction retained. Now if we had our 75 millimeter sieve for this example problem, we sieved our entire sample through that screen. The fraction retained is simply just the fraction in class. And working down the sizes, what the fraction retained would just be the fraction we saw in that class plus the sum of everything above it. Right? That would all get caught in the screen. So using that relationship, we get the fraction retained. Alright. Now for fraction passing. So if you're working in percent, you just do 100 minus the percent retained. We're working in fractions, so we are just going to do 1 minus the fraction retained. All right, so now let's look how we're going to fit these equations. Opening up the lab and scrolling down to the equation sheet. As we discussed in class, so what we're doing, we're taking this nonlinear equation, we're transforming y and x, so it's a line, and then we're fitting a line. Right, so first let's transform y and x, and then we'll be able to solve for m here. First thing I'm going to do for sieve size, and remember this isn't the average size, it's the size for that class, I'm going to put an x. So that's our x. And for fraction passing, I'm just going to put a y here. So before transformation, any kind of log transformation, that's our x and our y. If you see an x or a y in these equations, for specifically the Gauden-Schumann and Rosen-Ramler, that's what you're going to use. So now let's transform, just take the log, natural log of these values. Alright, so ln of x. That's simply going to be ln of our sieve size. And we're going to drag that all the way down. You don't take the ln of pan, obviously. You're just going to get an error. And we also need ln of y. And that's just the fraction passing. All right. So now that we've taken the ln of x and ln of y, we're working with this linear equation. As you can see, m, it's the same m as here, is just like a slope in a line. Here's equations for fitting a linear equation given a data set. You could see for the slope here, this b1, it's the covariance of some x and y over the variance of x. So we can do this in Excel pretty easily. And you could see that that's what this equation ends up being. So for our fitting constants, I'm just going to put gs here, and we're going to find m and k. So for m, we need to use the function in Excel covariance dot s. That's the covariance of our sample. And our so-called x is this ln of x. And our so-called y is this ln of y. So you add both of these columns to the calculation. And you should get the same covariance if you're working with the example data set. And we're going to divide that by var.s. That's the sample variance. And we're working with the log of x here. So the log of x is like our x in the linear equation. All right. So we have our m. For k, I think the easiest way in Excel is to use this formula right here. It's a product of all the x's, or the sizes, it's the geometric mean of them, over the geometric mean of the y's, but kind of weighted by m. So the geometric mean of the fraction passing. And these x's and y's are before we take the transformation. So to do that, let's just work on the numerator first. We'll need to do the product of our x's and we take that to the power of 1 over the total number of data points besides the pan. So in this case, it's going to be seven. Divided by 1 divided by count. Alright, that's our numerator. Our denominator is another product, and we just use the fraction passing here without the 0. We'll also be dividing by 0. And we take that to the power of 1 divided by m times n again. So the count which should be 7 in this case. You can just substitute 7 in your spreadsheet if you'd like. And making sure I have enough parentheses, hit enter, and we have k. Alright, now for the Rosen-Ramler equation. For the Rosen-Ramler equations, we end up taking a little more complicated transformation of y, but we still use just the natural log of x, and we end up with the natural log of r. So I'm going to make another column here. It's going to be, if you look at this size modulus equation, unfortunately I made a typo. This k should be r. We're going to need to take a product of the negative natural log of 1 minus the fraction passing, or the fraction retained. Instead of 1 minus the fraction passing, you can just use the fraction retained if you'd like. But to keep it simple, I'm going to use the fraction passing. So I need to do negative ln 1 minus y. And that's going to be negative ln 1 minus the fraction passing. And you drag that down. Now the other transformation we need is for this, for m, this covariance calculation. For that, we need what's on the left-hand side here of this linearized equation. So that's ln negative ln 1 minus y. So to do that, we just copy that, ln negative ln 1 minus the fraction passing here, and we drag that down. So here we need m and r. For m, what we could actually do is we could just copy these equations down here, and then we're going to need to change where they're referencing. So remember, we have the same transformation of x, but we have this other transformation of y. And that gives us the right answer. And for r, we're still using the regular x. So we need to move this back up. But for the y's, we're using just the negative ln of 1 minus the fraction passing. So we need to move these references over. All right. Now, if you're worried about whether you typed in the equations right, one thing you could do is you could highlight the ln of x and the ln of y and make a chart. And these steps will be slightly different in Excel. I believe if you click on the points, insert trend line or something along those lines, you want a linear regression and show the equation. So here's our m. Right, we have a linear equation. This is our m. And this intercept here, this negative 0.977, that's equal to negative m ln of k. So you could take that 0.977 value, set it equal to m ln of k, solve for k, and that should give you the same value. However, for showing your work in the lab, I'd like you to either submit your spreadsheet with the PDF document or a printout of your spreadsheet in PDF form. Either one's acceptable. I would also recommend for some of the discussion questions, especially in interpreting some of the reasoning or meaning behind m and k, as well as m and r, to look at the video for making the plots in R, starting at about 15 minutes and 50 seconds. I go over some valuable information for answering some of the discussion questions, as well as further insights. All right, as always, if you have any more questions, definitely contact me, and I'll see you in lab.